limitations of the wave model of light when applied to the photoelectric effect. Okay? Well, the limitation is the photoelectric effect. If light is behaving as waves, then any amount hitting the metal should cause the photoelectric effect to happen. The fact that only certain energies worked, only certain wavelengths or frequencies worked to cause the metal to eject electrons and create a current is the photoelectric effect. So the photoelectric effect tells us that light isn't always behaving like a wave, or EM radiation isn't always behaving like a wave. Okay? That hint is really pretty telling on that one. How are energy and frequency related? Well, that's the other equation. We have the equation for the speed of light. Then our second equation, E equals hf, or E equals h nu, the same thing, frequency as f or nu, either one is fine. Energy and frequency are directly proportional. If it's a higher frequency, higher energy. Ultraviolet light, for example. We're worried about UV rays hitting us in the summer or anytime because they're higher frequency waves, they have higher energy, they're potentially more damaging to our cells than infrared or anything lower. And you know what H stands for? Planck's constant or Planck's constant. You might want to jot that on your exam cheat sheet. 6.63 times 10 to the negative 34th joules seconds. That's joules times seconds. Number 10. How wavelength, frequency, and energy of waves in the Paschen and Balmer series compare. Oh my gosh, what are the Paschen and Balmer series? What element are we talking about there?
Hydrogen.
Hydrogen, yes, the one we studied ad nauseum. So it's the Lyman, Paschen, and Balmer series. And one of them has higher energy than the other. Okay? Did we look at the chart in our book? Do we know the difference between them? Okay, well that's something you should be looking at in your book, studio audience. And this will be in general, you know, is, Paschen higher energy or lower energy than Balmer? Is it higher frequency or lower frequency than Balmer? Check that in the picture in your book. Somebody want to find that page real quick? Somebody that has a book, some well-prepared student? I'll give my voice a You're diligently looking. You never use your book. What?
In class.
I now have that recorded.
That was
Yes.
Josh.
What page?
98.
Page 98? Is that the Lyman, Balmer, and Paschen series?
No.
This is
What is it?
101.
101. And which one is the highest in energy?
Posh. Wait.
Paschen.
No.
Which one has the biggest jumps?
Oh, Aegis jumps?
All the way back to level 1.
Wait, wrong page, wrong page.
Okay, we're still not sure of the page.
103. As I said.
What page?
103.
103. And the biggest jump is Lyman, and that's from upper levels to level 1, right? And from upper levels to level 2 is Paschen, Balmer. And from upper levels to level 3 is Paschen, right? So, which has higher energy? Lyman, then Balmer, then Paschen. Okay.
What about? Oh, just kidding. So then from that we can figure out the wavelength and frequency.
Right. It's a general comparison. It's not. And number 11.
Yes.
How a bright line spectrum of an atom is produced specifically. Okay, this has been the key component of all of your summaries on all of your labs in this chapter. Electrons and atoms get excited by radiant energy, heat or light. They jump to higher levels. They cannot stay in that excited state further from the nucleus for very long because they move ridiculously fast and they're attracted to the nucleus because of charge. So they spit that energy right back out, and that's when we see a line in a bright line spectrum. It's very specifically when the electron is falling back to a lower level. And something else I want to clarify based on the summaries I've been reading. An electron doesn't jump up to a higher level and then automatically go right back to where it started from. Okay? When one electron jumps to a higher level, another one fell down and took its spot. So maybe our initial electron has to jump to a different level. They go to the lowest level they can if there's a spot available, if there's room available that close to the nucleus. But they don't just necessarily go up to level A and back to level B. They may go up to A and then back to C or D or whatever. Okay? Are we good with that? Because it's not just that they go up and fall right back down to where they were. They just go to a lower state. It may well be right where they were, the same energy level, but it could be a different energy level as well. And number 12, what the Bohr model of the atom was trying to explain. It was trying to explain why hydrogen did what? Bohr was trying to explain why hydrogen did what? When it was excited. Gave off what? Gave off light of those specific colors. Why was hydrogen only giving off that red, turquoise, blue, and purple line? Why wasn't it giving off all the colors? Okay. How come there was that specific bright line spectrum pattern instead of all the colors of the rainbow? And let's do one more. The definition of ground state and another name for it. Ground state is the lowest energy state for an atom, and it is not an excited state. So excited state would be the opposite of that. Okay, so lowest possible energy state or ground state. Those two terms are used interchangeably. Okay, and that does it for the first half of the test hits.